get started, but I avoid math problems like a plague.
When did you do the questions 2 and 3?
I am working on it. I'm almost finished with that one.
How hard is that one?
I'll tell you over break.
I kind of started, but not bad. Kind of looked at it, I read the book some, but then I saw the math. I was like, you know what? It's gonna make more sense.
I just kind of studied for this midterm, but then when I looked at the slides, I'm like, oh crap, here we go, getting confused. I just skipped Thursday's seminar to UCSC 200. I always skip that class and always have someone giving me the information. And I don't like that class. It's really good nothing.
It's kind of general information for being a TA.
I know, plus the research, plus finding your advisor for your thesis, and get me to be like, dude, I already know all this thing already. Skip class. But I never skipped this class. This guy's good. I'm like, you just said skip this class, you must have guts. Man, look at my notebook. Got wet. It got wet because I was walking at 6 a.m. in the morning and was totally raining. I was literally soaking wet. So I had my raincoat, I'd be crying.
It's really wet today, yeah.
Look at this notebook. It's like beat up already. What the heck?
It's a little dry out though. Avoid the wet bits.
Rip. Who should we ask for editing?
Whoever wants to get it, honestly.
You're aroused. Hey guys, who is going with the like a rally. Hey, who's going with the
Was the announcement fake news?
No. I'm just recording it just for so I keep track for next year of what and I'm gonna put some just the slides with the EM just to have it for reference. But no. We'll see for now.
I don't want to say I'm rude. You go attend the union?
The what? Today? Yeah. I can't. I left class.
I mean, you can because I'm trying to stay on campus for the whole day. It's just because those neighbors, obviously.
Music's on Zoom, isn't it?
Huh?
Music's on Zoom.
Where? Because it's the science room.
So can everyone hear me? Can we start? So this will be a special class, as I announced last night. So I know I connected on Zoom, but this is not meant to be a Zoom class. Actually, so there's like 3 or 4 people I saw on Zoom. I will be doing exercise on a blackboard, so it won't be. I won't be able to. I don't know. I'll be trying. I don't think it's going to work that well. I don't know if you can see from the laptop camera on the blackboard, but yeah, it's not meant to be a Zoom class. So thank you for coming in person. And what was I going to say? A few things. Oh yes. So I want all of you to come a bit closer, to come on the front row. So especially those on the back. So I want you to kind of like fill up more the front row so that you come a bit closer. So at least for today and for Thursday as well. So I want people to come so we can see better. Okay. There's a few seats here in the front that are more free, so you can come in these ones.
I like read the book some yesterday and I was
For me, I started on the programming one where I was
So
you have to do it on scratch.
we have a few people.
It's the linear regression, but 2.0. It's really hard.
So I got some feedback from some of you. So as we were talking about last week, we wanted to do some more exercises for today and for the next week. So actually for today, we're going through do some of the derivations of the EM algorithm, which will help you towards your first question in the assignment. How is that going? How is the first assignment going? How many of you have solved the first question? Nobody.
I'm solving the second question.
What about the other ones? How many of you have done the KME's implementation?
Almost done.
Nice. And the other exercises?
Don't want to touch.
So actually the first problem is harder. So I would even recommend like do the other ones first and come back to the first one at the end. But we will go through some of this today in the class. So do ask me any questions we have. I think it's important to do these things because these are some key fundamental concepts that we want to solidify in the class. And I know it's sometimes a bit more than what you normally do in this course, but it's very important in machine learning. And these kinds of ideas, we'll see it applies again to many other models you'll see later on in other courses you'll take. So let's remind ourselves, which is why I put like still connected to the Zoom and then have the slides. What the setting was about in EM. So in EM we had data points that were not labeled, and we had to find clusters. Like for example here, a green cluster, a red cluster, and a blue cluster. So this was our setting. I haven't connected this. So let's remind ourselves a few things. I wanted to start first by I wanted to ask. I'm asking you in the audience, what is the graphical model of the Gaussian mixture model? How do we start? So, and we have these equations as well later on. So we have this. But what is the graphical model? So let's see what that means. So I think it's such an important concept that we want to make sure we understand this. So the graphical model for this scenario and is that we have so first we have a prior distribution pi, which is where we sample from, which is like the mixture of the it's how many, which says like how many points are in the green cluster, how many are in the blue cluster, and so on. Then we sample a latent variable z, which is it's basically the label of data point I. It's basically in which cluster does data point I belong. And then we have data points xi. And from this, we and to generate data points xi, we don't need just the cluster, but we also need the parameters of the Gaussian distribution. So we need the mu and the sigma.
You said pi was what again?
So pi is are these. In our slides are the thetas basically. Sorry for the notation, for the difference notation. I'm using the same notation as in the assignment. So pi is basically a vector that has. So for example, this is pi red, pi green, and so on. It's what proportion of the points are in each cluster. So it's this is what pi represents, or also theta. So theta is what we use in the slides here. So for pi. Yes. So this is how the graphical model looks like, and the key idea is that we do this. I'm putting a box, and we're doing this for all data points from 1 up to n. We repeat this because we sample multiple data points, multiple labels, and then the actual data point, multiple times, n times. And then we also do this k times for each cluster. So we have a mu1 up to mu k, sigma 1 up to sigma k. So this is the graphical model of the Gaussian mixture model. And what this means is that the way the distribution factorizes, it follows exactly this graphical model. So more precisely, what this means is that when we sample all these variables, we essentially, instead of it's the probability of having a pi, comma z, comma x, comma mu, comma sigma, will factorize as pi over pi. So let's write it out. So the pi over pi z, x, mu, and sigma will factorize as, we first start with the ancestor which is pi. Then we sample the next one, z given pi, given pi, times p. Then we do priors over these, for example, pi over mu, pi over sigma, and then what? How do we do this term of x? How do we take the x here? So we do a node given its parents, given this is x given z, mu, and sigma. This is p of x given z, mu, and sigma. This is how it factorizes. This is what it means. It means that with this graphical model, it means that this distribution factorizes like this into these terms. So this is kind of like more like I'm trying to lay a bit of foundation to understand a bit more like how these things are done. But does this make sense so far? Yes.
What is the third term set?
This one or this one? These ones. These are priors over the means. This is a prior over the mean of the Gaussian distributions.
No, I just can't read the.
Oh, p of mu. Yeah.
It's p of pi times p of z given pi, then times p of mu times p of sigma, right?
Yes. P of pi times p of z given pi. P of mu. Yes. Can you read it? Can you read it also on the back? Yeah.
Even the prior of x is multiplied. Right?
Sorry.
Even the prior of x is multiplied.
In the first equation.
Why is the prior of x multiplied?
I'm asking if it is multiplied.
So is it p of sigma times p of x given z, mu, and sigma? Is this all one continuous formula?
Yes. Oh, this is all like multiplying with each other. So these are all multiplications. How many of you are with me so far? So how many of you understand this? Not too many. So some, okay, some like 25-30%. Let me give an example, a simple example. Imagine you have, imagine you're trying to. So this is like, imagine we take like a health network, and let's actually do it here. So imagine you're trying to predict tuberculosis. You have a node of tuberculosis. For example, a diagnosis given that you have an X-ray scan and that you have a particular gene and also we have the X-ray is given by the age. So let's take a simple graph like this, graphical model like this. So what this means, and you see we also have nodes and we have arrows, the same way we have all of these are nodes. And an arrow. So what this means is that the joint distribution over all four of them, so P of A, comma X, comma T, comma G. So the joint probability of age, X-ray scan, tuberculosis, and the gene is factorizes as we start with the parent. So it's this P of A, prior over A, times prior over G, times what else? X given A, exactly. And what else? T given X comma G is X-ray. So this is what this structure means. It means that this joint probability factorizes like this. So you can write it as such. Let me move to that side. So when we have this so this is actually an important concept of a graphical model. So we have a graphical model for the EM algorithm, which is for the Gaussian mixture model, which is exactly following exactly those principles like that. So to take an again, if we have a Markov model, for example, not even a hidden, just a simple Markov model, we have so I'm doing another, so I'm separating it out. So if we have, for example, let me do it here, x1 implies x2 implies x3 like this, and so on. So this is a Markov model. This one only depends on the previous, on the one from before. So we can write the joint distribution of, let's stop here, so of P of x1, x2, x3 as what?
Probability of x1, P of x2.
Exactly. P of x1, P of x2 given x1 times P of x3. Exactly. So let me do this x2 comma x1. Let me do this. You can always write a joint distribution like this. You first start with x1, then you do x2 given x1, then x3 given the previous two. You can always write any distribution. The fact that it has the Markov property, it means that x3 is not dependent on x1, conditioned on x2. So actually that means you can cut out this term. And that's what it means that, and then afterwards you just get P of x3 given x2. So essentially the assumption is that we get rid of these variables. This is independent. Like x3 is conditionally independent of x1 given x2. So that's another important concept. So this is why we can write it as this then, P of x3, which is what we've been doing so far. Because any distribution, we could have written it like that if we included also another term. Does it make sense so far? Okay, any questions still? Any clarifications? Yes? For this formula? This one? A single line, yes. So it doesn't fit. Yeah. Any other questions? Okay. So let's start with the EM now. So now given we know this, because we'll use this, we'll start with the EM. So remember we were saying in the class how, and I'm bringing a bit this slide again, how when we're talking about this slide, when we took this log likelihood of x given the parameters of the model, the mu's and sigmas and the thetas, which are the pi's here, from the assignment, that this is hard to do because it's hard. Sometimes it's hard. You have this log term. You take the logarithm of it, but you cannot put the log inside the sum. We're talking about this and how it's actually harder to optimize this. You can still optimize it, but it's much, much slower and much more inefficient. So, so what the EM algorithm does is that, so we have log of x given pi, mu, and sigma. So I think this was the notation in the assignment of but whereas that one is from the slide. But what we're trying to do is we would like to optimize this, the likelihood. So this is, what is this? Actually, is this the log likelihood? Yeah? It's the likelihood of our data given the model parameters. These are the cluster means, cluster variance, and this is the proportion of data points to each cluster. Yeah? Sorry? This is the log likelihood of the model. This is the log likelihood of data x given parameters, given the model parameters. This is what this is. So remember, and always when we were doing in machine learning, even in a linear regression, we had a likelihood function that we were we were optimizing, and we had like the error terms, the squared error terms, and we're taking the likelihood of that. So we had the same thing. So we always optimize the likelihood. Yes.
Just looking at the slides, why isn't it the log probability?
Sorry. Yes, it's the log. Yes, log. This is log p.
And this is just the function that we call L, right?
Yes, yes, yes. So this is log probability of x given. Sorry about it. That was a typo. Yes. So this is what we're trying to optimize. So always in every model, not just in this case we have a Gaussian mixture model. But in any model we try to optimize generally the likelihood of our data given parameters, given the parameters. So so we're trying to optimize this, and we saw in the slides how it was hard, and the reason it's hard because that summation, that the logarithm doesn't go within the doesn't go here inside the sum. This log doesn't penetrate the sum. So what the trick with EM is that instead of optimizing this, what we optimize is let me use another color. Is that we also add the latent variable z, which are the assignments of the points to each cluster, which are the sort of like the inferred labels that you can think about. And then so we do that, and then instead of doing that, because we don't know them, we have to marginalize them. So we do the expectation with respect to z given x mu sigma pi. This is like this. So I write it like this. So now we take so we added z, but we have to take the expectation over z to marginalize it, and this is the objective that we optimize instead in EM. So instead of that one, we optimize this one instead. So and the key thing we do is that, of course, we want to maximize this with respect to the parameters. This is what we always want to do. So we take the argmax with respect to pi, mu, and sigma. These are all our parameters from here, yeah? And these will be our new pi, mu, and sigma at iteration t+1. can barely fit in. Can everyone see?
No, what's that again? Far left.
The far left is
Yeah, I'm just seeing it.
left is the equal sign is kind of like
Let me simplify it a bit. Let's do just one parameter. What if we just do, we want to do just sigma, with mu, sorry. We want to just find the maximum over mu. So we're trying to find the maximum of our parameter mu, mean. And then we do, this will give us a new parameter at the next iteration at t plus 1. Yeah? So doing this iteration once.
So doing expectation on that formula?
Of this whole thing, yes, yes, yes. Sorry? So remember with the EM algorithm, we always do iterations. We do iterations, and at each step we update these parameters, right? Like at each iteration we update our mu, our sigma, our pi, basically. So this is from iteration t plus 1. Let's add the iterations. So these are at iteration. No, these are not bound to, because this is what we're trying to maximize. For example, over these. But these are from these ones are from the previous iteration. T minus 1, t minus 1, t minus 1. So each of these in the expectation are from the previous iteration. And these ones are the ones that we're trying to optimize.
It's for the iteration t plus 1 or for t? Well, if it's t minus 1, it would be for iteration.
For t, in that case, yeah. Is everyone with me so far? Yeah? Any questions?
So how does marginalization is helping us?
When you don't know a variable, you sum over it, because if you're trying to optimize p of x, for example, you can always do this. You can always, this is true for any random variables that you introduce. You can always introduce a variable and marginalize over it. So you sum over all the possible values of z, and you can always do this. And you always choose a particular z that is helpful to you towards your objective somehow.
That's what that z is.
Yeah. So the z is again, in our case, these are the inferred labels of each data point. But again, I don't even want to call them labels. I'll call them assignments to clusters, because they're not labeled by a human. They're inferred. Yes. So let me yes, okay. So so how do we does this so what do we do in the E step given here, given this? What does the E step tell us to do? Get the expectation. Say louder.
Calculate the expectation of given the
Almost. It's even simpler than that. It's just computing this distribution, this p of z given that. It's just computing that. That's all it does. The E step.
In short, we are calculating the expectation of assignment of clusters.
Yes. Of assignments of points to clusters. Yes. but let's take this equation and like let's try to manipulate it a bit instead of simplify it a bit. So let's try to simplify it, because let's try to understand what is happening here. So so I won't take the R max for now. I'll just work with this right hand side, the expectation and the rest. So this let me call it omega, some number. So omega would be equal to what? So what's the formula for the expectation? I hear some, yeah? From the back. I want to hear some answers from the back as well. So what we do is we plug in the formula for the expectation. So let's go through it again. So E of x is sum over what? Sum over all the x's of x times p of x. Yeah, that's the formula for the expectation. Sorry? Thank you. How about now? Can you see from this? Okay. So that's the formula for the expectation. So we plug it in here. So the expectation over that is, so we sum over this entire distribution of z's. So, and what are the z's? Remember, so is z like for a single data point here? Yeah, I heard something. For all the data points, yes. So we have z's for all the data points. So actually we have to sum over. So I'll write it explicitly for at least a bit. So we have z1, z2, zn. So this is what we're summing over when we do all of this of p of this is what z is, z1, comma z2, zn, given x1, xn. When we have n data points and z's, I wrote them explicitly. Mu t minus 1, sigma t minus 1, pi t minus 1 times log of this. So what is this? How can we what do we do with this to simplify it a bit to this structure? Yeah, we exactly. So we use the graphical model. So we expand the factorization and then
the equation on the top.
This one. Yeah, exactly. So notice how we have p of z given pi times p of z x given these. So we can use this. So you see, like p of z comma x given these parameters is this term plus this term. Yeah. From the independence assumptions of the model. So let's write it like that. So we get p of z given pi, p of x given z mu sigma. Yeah? So this is a pi.
That's all in the log?
That's all under log, yeah. Yeah? I see you're confused a bit.
explain again the first part of it, the P of Z1, Z2 to Zn?
Yes. So what is happening is that this Z, this is Z, is made of many data points.
Yeah.
So this is a multi-dimensional distribution. So I'm just expanding it. It's the same as before. This is the same as this structure, exactly the same. It's just written out, expanded, like this. I wrote it like that to sort of highlight that this is not a single random variable. We have n different random variables, Z1, Z2 up to Zn, and X is the same. This capital X is the same. It's a big. It's a joint again. It denotes all the data points. This capital X, all n data points. So x1, x2, xn. That's why I wrote it expanded. And the same for mu. So mu again, it refers to all the mu's for all the clusters. Mu1 up to mu k, sigma 1 up to sigma k, and so on. Yes, we have a question there.
Can you go over the different versions of mu, sigma, and pi in the different iterations again?
Can I go over the different versions? I'm repeating the question. Can I go over the different versions of mu, sigma, and pi? So they are. You have one of them for each cluster. You have mu1. So
I mean, just in the equation, right? Because there's like mu plus plus, mu plus, and regular mu. I was wondering what.
or here.
T minus 1, T minus 1. Oh, T minus 1.
So these are from iteration T. Do you want to come closer also, because I don't know if you can see. It's from iteration T minus 1 from the previous iteration. These ones, and they're fixed. And these are the ones that we get at this iteration T, for example.
And which iteration are the ones on the right from?
Yes. Sorry?
Oh, which iteration are the ones on the right from?
They are from this current. So this one. Let me do it a different one. So this one maps to. Like this, to this one. So this parameter that we optimize maps over this one. So that's why it's not, in some sense, only when we maximize it. This is like a free parameter that we're maximizing over, and only when we find the value that maximizes this function, then we store it as the next one at iteration T. Does it make sense? Yes.
Can you explain again how you went from the likelihood on the top to the likelihood on the bottom?
Yes, so from here to here, I simply wrote out the formula for the expectation. So I applied this formula here. So I applied expectation over distribution x is x times p of x. In particular, there's even a more, I suppose, even a more accurate formula. Well, not more accurate. It's just I applied the formula of expectation over a function, though. So let me write that as well. So we have the expectation over f of x. So if we have a variable and we apply any function to it, then this is just like this. We sum over all the x's, and then we do what? What's the formula for that? Someone from the audience. What's the expectation over a function of x, f of x? X times p of x. That's the same as this one.
F of x times p of f of x?
Times p of f. So no. So very close. It's f of x times p of x. Just that. We always take, yes, we. Yeah. And let me flip them around so they're consistent with this. So it's p of x times f of x. So I just flip them around. So now you see, instead of, oh gosh, now no.
No, it was consistent before.
It was consistent before. No, my bad. F of x times p of x. Yes. So for in a case where the function is identity, f of x is equal to x, then we get this formula from the left.
Okay, gotcha.
So I applied that formula. So here, in regarding to the question I got, I applied that formula, the expectation over a function, when f is a log. The function is log here.
I just don't understand, like, within the log, how you got
Oh, I applied another step. Yes, so from this is the joint over x and z. Remember, yes, now I got your question. What I did there is I used this the fact that the joint over x and z factorized like this. So you first sample z given pi, and then you sample x given its parents. That's what I did. I used this structure from the graphical model of the mixture model. So let me forget about these conditionals. What this means is that p of I'll write it very small here. P of x comma z is equal to p of z, p of x given z. I didn't write the other terms, but this is. Do you see how p of x z is? You first sample z, then you sample x given z. But there's some trailing parameters. Z is dependent on pi as well. Z depends on pi. X also depends on mu and sigma as well. So that's those just stay there, like because again from this structure, look, x depends on z, mu, and sigma. So you need them as well. But this is what I applied. I applied this little thing.
When you say x depends on mu and sigma, I understand that mu and sigma can help define which cluster it goes into, right?
Because x, remember, x is sampled from a cluster. The model assumes that we choose a z, we choose a cluster, and then we use those parameters. So we choose zi, which is a k, a cluster k, and then we use mu k and sigma k to sample x from that cluster. That's why it depends on. Yeah? The question.
So we got the equation for omega, where z takes the value of each data point, right? And then the parameters take the value of each iteration. And I'm trying to understand. Yeah. So then we have the data points, and then we have the iteration. But in the second part where it's the log, in the second
Here,
part,
yeah.
I'm trying to understand. We have z, which can have a specific data point value, but there it has nothing. It's just z, and I don't get it. Like if z has a probability density function, then what goes there? Like what is z in that part?
What is z here? P of z given pi.
Yeah.
So the p of z given pi. So is your question is what are these functions? What are they instantiated with?
I don't understand probability of z given pi. I understand probability of a data point given something.
Yeah, so p of z given pi is basically the likelihood of sampling all the z's. These z represent all the z's, z1, z2, zn given pi. So for example, and because they're independent, you can do p of zi given pi. So you can see independence, for example, and then p of zi given pi is simply so I can write it even more precisely like this: p of zi equals forget about let me rewrite it. So p of zi given pi, I can write it as p of zi equals k given pi. Yeah, so for example, what's the probability that zi equals to a particular value k, a particular value, for example, let's say 2 or 3, and that is exactly pi k. So remember, pi is a vector of pi 1, pi 2, pi capital K. So it's the proportion of like points in each cluster. 20% in cluster 1, 30% in cluster 2, the remaining cluster 3, for example. That's what pi means. So the probability of sampling a point from cluster K, given our vector of all these pi's, which is what this means, is exactly, for example, if this P of zi equals 2, then we just say this is a pi 2. So then we should just take this value, and that's the probability.
All the possible values of z right there.
Yes, that's why we do this. We do because it's in the independent. Yeah, that's the product. So the probability of all those. What this means is that it's written in shorthand notation, but this means that the probability of z1 being equal to a k, z2 being equal to a k prime, z3 being equal to a k double prime, and so on, would be a product of all of those. Yeah? I think there's still some people that are a bit confused. Well, what any other questions? Or does this make sense?
Why do we calculate the expectation?
Why do we calculate this? I'll show you at the end. I'll show you after we do this. I'll get back to that. That's a harder sort of thing. We'll have to use a bit Jensen's inequality for that.
Okay.
I'll show you. So just assume for now you have to optimize this, and I'll explain later how we even get to this. Is this clear? How we got from this to that, this factorization and so on, and how this revises? Okay, so. So there's two things we do next. I'll do two steps. The first step is that I'll rewrite omega. So one thing you can do here is that this sum over all the z's, you can basically so this P of z1, z2, zn is can be, again, we assume this independence, and actually no, let's leave that for now. Let's take it. What I'll do is the following. So I'll do sigma equals the same thing here, but now instead of log, so when I do a log, I'll do this. So here I want to break into multiple zi's. So now I'll assume independence across data points, which is based from our graphical structure, because these are all independent. So the next thing you do is that you write, this is a log of a product from I equals 1 to n of p of zi given pi. So using this times p of xi given zi minus sigma. So I did a product from all the data points 1 to n of p of zi given pi. So it's the same as before. Now I assume independence. So I essentially do a product over all the zi's, which is this joint is equal to product over all the individual probabilities. Yeah, and this also, and this becomes, and if I flip the log with the product, right, in a log of product, log of a times b is log a plus log b. So then this, I can put the log inside, and this turns into a sum. So this turns into a sum from I equals 1 to n of log of p. So sum of log of p of the rest. zi given pi, p of xi given zi mu sigma. The same thing. So the only thing I did is I put the log inside, and this turns into a sum. Yeah? Make sense? Okay. So the next thing I'll do is, I guess I'll use this part here. Is that I'll move this sum all the way to the beginning, which is something in this. So this is like, and I know some of these are a bit complex to understand, like why when you work with these sums and products, why you can do this. But it's a factorization that you can do. So you can. So the next step is, if you realize you can always put the sum. So I'm moving this sum from I equals 1 to n to the beginning. And then I start, with sum over z1 up to zn, all the z's of p of z1, zn, given. I won't write the x's for now. Mu sigma pi times what? Times log of p of zi given pi, p of xi given zi mu sigma pi. And let me know if I make any mistakes, okay? Which I could make. So the key thing I've done here now is that I moved this sum all the way to the beginning, and now it appears here. And this means that we do the sums in a different way, but they come out to the same result if you write all the terms and do the maths. So this is starting to look a bit interesting now. You see now that we move the sum. So now we have, because we kind of have almost like the sum over all the data points at the beginning, which is kind of what we want. We still have this crazy sum here, which we kind of have to do something about, because it's over all the z's. And this distribution, what can we do about this? It's not looking too nice. It's like all those z's, all those x's. What do we do with it? It's the same. So big X is x1 and comma x2 comma xn. So I'm using more like shorthand notation, but I wrote it here at least to make sure this X represents many random variables.
There's so the X's are data points, right? The x1. So there's not necessarily the same number of clusters as there are data points, right?
Yeah. Yeah. So X's. So the question was there's not the same number of data points as clusters. So the data points go from 1 to n. The clusters go from 1 to k, to capital K.
For z, should we be saying z1 to zk then instead of z1 to zn?
No, because there's n data points, but each of these can take a value from 1 to capital K.
I see. So there's n assignments for
n assignments for n data points.
K values.
Each z can be 1 or 2 or k, capital K, which denotes the cluster.
So A is the number of data points.
N is the number of data points here. Yeah. Yeah. Exactly here. So we can assume again independence across data points because we have that each z. So and what this means exactly? Do you know what this structure here means? That we have the same thing cloned multiple times. So basically, it's like imagine you have another box here. This is for z1. We have another box of z2, and so on. So they will all be independent from each other. Like they don't influence each other. They only just depend on pi. That's it. That's what this structure means. Is we have all these cloned n times and different such structures repeated. So we assume independence here, so we can break this apart by assuming independence across the z's. That's why we can, because we can assume independence. So this becomes pi equals sum, I equals 1 to n, sum over z1 zn of yes, and I'll choose to break it apart so we can, you'll see in a particular way, but you can write it like this. So you can do the product again from, well, I can do that like P of Z1 given x1 mu sigma pi P of Z2 given x2 and so on P of Zn given xn mu sigma pi. Yeah, so it's just breaking it apart for each z, assuming the independence. So what I'll do is that to see how you kind of have to get rid of. So what you'll see is that over here we have just zi on this side. So what we kind of want is to separate the zi from this. We take the ith term, which corresponds to this index, and we push it in the front, and we separate the rest. This is the key step you kind of have to do. So so this becomes sum over I, sum, and here's what I'll do. So I do a sum over zi and do P of, and I separate zi given xi. So I sum just over zi first and do P of zi given xi mu sigma pi. And the other terms I push them later on. So and then I can do these terms. I can do the log P of zi given pi P of xi given zi mu sigma pi. Okay, so I separate the zi sum and the zi term, and I'm still left with all the other ones, so I can push them to the end. So here, and so I do times sum for all so how should I write this? I can write sum for z1 up to zn, but different from zj. So here what I'm writing is all the z1s up to zn, but apart from zj, which I no, sorry, zi, sorry.
So that first sum zi really isn't a sum, it's just zi, right?
No, because you have to sum, well, it's like all the values zi can have. So it's maybe you can write it as like sum over k of clusters of the values that zi can take. Zi of P of zi equals k. This is what that means.
Got it.
I see. So some people are confused. Yeah. So when we sum, let me take a simpler one. Let me take here. Let me explain it with that. So when we do sum over x of x times px, what this actually means, capital X is a random variable. What this actually means is, so I'm doing a step. So what this means, this is equal to sum over small x. So notice now I have a small x of small x times P of capital X equals small x. What this means is that you sum over all the possible values that the random variable x can take, and then you multiply that small value with the probability. So there's a probability that capital X equals 3 or 4 or 5. This is what this means. So you sum over all those values 3, 4, 5, 6, 7. That's it. So here, P of zi of this means that you sum over all the possible values that zi can take, which are 1, 2 up to k. Zi can only take these values 1, 2, or up to k. It's a cluster. It's the cluster that data point I belongs to. you can write it like this. You can write sum over k of p of zi equals k. I can write it like this. P of z p of zi equals k. Do you understand this? Oh, so you mean this? I mean this. Oh, sorry. I was explaining the other something else. The summation. So basically, we had this multiple sums. You can push them. This is not an easy step. I think I'll need another board to understand to explain that.
It's kind of like given all the z's, you're just factoring out the height z.
Yes, yes. It's like a distributivity sort of operation. You're factoring them out. Wait, how many of you? Let me write it out first. And I'll come back to it. So you do the sums of all the z's. So I push them in the front of all these terms that are left. So p of z1 given x minus sigma pi p of z2 and so on.
z1 given x or z1 given x1?
Sorry?
Just given x.
Yeah, x1, yeah, exactly. x2 and so on, yeah, and xn minus sigma pi. Exactly. So these are the remaining sums apart from this term. These are all the remaining ones. So this is because we factorize only. We factorized these terms and by pushing them in the front. This is what we did. How many of you understand this step? Because it's a hard step. So raise your hand if you understand it. I can do a small example. Shall we do a small example? Yeah. Or
it's slightly confusing is we're not understanding like why is it summing for k? Like why is it
put it back to z1 or zi. Is that That's the same.
Why is it summing over zi and then also summing over all the terms that are not? So isn't the sum for zi just one term? That's what's confusing me.
I think the inner sum for zi is kind of one term that we've pulled out of this other sum.
Oh, so it's just one term.
Yeah, so
It's one term that we
It's
it's one term.
just one term.
But it's a sum over zi.
Over the zi values of equal and k though. So the bottom summation is across every assignment to a data point. The top one is for just one data point, but out of all the clusters it could be in.
Let's take an example. I think this is best understood if we take a small example. And I think so imagine we have the following. Imagine we have P of, let me think. So imagine we do over two variables only, and they take only two values. So what is the sum over z1, comma z2 of P of z1 given x1, P of z2 given x2? So what is this? What if you have just two variables and z1 comma z2 belong in can take only values 1 and 2, for example, or even 0 or 1. So only two variables and only two values for each. Yeah. So what is this sum? So this sum is
1 given x1 and 1 given x2. 2 given x2, and then 2 given x1.
2 given x2, yes, yes.
2 given
So this is what the sum is. So it's p of z1 equals 1 given x1, p of z2 equals 1 given x2, plus, so 1, 1, then we do 1, 2, z1 equals 1 given x1, p of z2 equals, so now I do 2 given x2.
Our sigma zi is iterating over our values of z, in this
Yeah.
case 1 and 2, and then our sigma z1 to zn is iterating over our z's. The number of different things that we have.
P1 is equal to given x1, p of z2 equals 1.
So then, quick question.
Yeah.
On that one, shouldn't it be a plus on that sigma and not a multiply?
Is it call?
Yeah, no.
I don't know. Oh,
If it's important, we'll call back.
yeah.
Shouldn't it be a sum adding that z1 to zn? Because you multiply it in, shouldn't it be
Oh,
between the two sigmas themselves?
in between here.
No.
It should be a one.
It should be
Just like it shows right there, right? Because it's like for z, let's say zi equals to 1, and you do it for all of those, right? 'Cause it's a bunch of, it's like from 1
Oh,
to n.
right. Yeah, right. Never mind.
Do you understand this? Do you understand how this comes? So you do 1, 1, 1, 2, 2, 1, and 2, 2. So this is what the sum means.
It would be 4.
Here it should have been
Yeah,
on
exactly.
K, right?
Sorry?
So here, if I transform this example to that example, where it is from 1 to K instead of
1 to k, exactly.
then why in the expression there is no K?
You can put k here. You can put, for example, again, I can put ki, for example, like an index for a k. So then I can put zi equals, this is a value k for the index. I can do that.
Value can go from 1 to
K, capital K, yes. Yeah?
That makes sense.
So the zi which is inside the log, it corresponds to the outer summation, right? That's it, right?
This outer summation or what?
The very outer one, right?
Yeah, exactly. So this I, exactly. This I controls this zi and these ones. All these are zi's, yes.
So, okay, so that I is also same for the first
Yeah.
here, which we have taken out. The first P of zi equals to K.
Yes, and it corresponds to that as well. So this I, the sum corresponds to this I, this index in the z. That's exactly why we're doing it, yes. So do you understand? So this is what this is. You can also write this sum. Let me show you something. So you can push one of these sums inside. This is equal to, because I haven't finished this example, sum over z1 of p of z1 given x1 times, and now I do another sum over z2 of p of z2 given x2. So what this means is that now I factorized these ones. I basically I factorized one of these terms here. You see, like I factorized this one. This one is factorized with
So in the expansion summation of P,
yeah.
I given x1 and P of that I given x2 as a fourth term, right?
There's a fourth term. Yes. I didn't write it. Yes, there's a fourth term. So there's a p of z1 equals 2, p of z2 equals 2. Exactly. So what you can do, you can take one of these, you can take this as to factorize using one of these terms, and you can write it like this. Then you factorize this with the rest. You can slide the sums this way. This is what I've done. I've slid these sums like that all the way to the end. All those terms. That's what I've done here. So these, all the zi's that were different, no, all the z's that were different from zi, I pushed them to the end. Okay, everyone with me so far?
No, I don't get how it becomes some
It's because you look here. No, I know. So I know. I think actually, if you get some of these things, it will help a lot. So look at this term here. Z1 equals 1 given x1. You also have it here. So what you can do P of this term given this plus that. You have A times B, and this is A times C. So we can write it as A times B plus C. This is what I've done. And this is what this means in sum terms. This is what this means. Yeah? Okay, so that's what we've done here. And now here's the magic here. If we push them to the end, these ones are just distributions. And because we factorize over them and we have nothing else, these all sum to 1. Do you see it? Because we sum over this one, we sum over or z1 over z2 and so on, and then that's it. There's nothing else.
Would it be 1 minus the ith term?
No. Well, let's look here. Sum over z2 of what is this term? We sum over all the values that this distribution can take. This term is 1. All the elements in the distribution will sum to 1. So this will be equal to 1. So then we have all of these times 1, which is all of these, and this will also sum to 1. So this sums to 1, all of this, all these 4 terms. Because we summed all the possibilities that we have. And it's a joint distribution, and any distribution will marginalize to 1.
So that whole last section.
That whole last section is 1. This is 1, this is 1, is the same thing that's happening there. So all of these terms, so all of this, including the summation, will be equal to 1. Yeah? Uh-huh. Gosh, I didn't realize it's already 11.
Do you want this to be a problem on the midterm?
Yeah, he's got tossed on the midterm.
I want to
No, it's for the assignment for now.
Keep it for the assignment for now.
Yeah?
Sure, he got tossed on the midterm. Low key.
Say it louder.
For the midterm, what kind of questions can we?
Oh, we'll talk. You might have something like this. You might have something like to do a part of this. No, we'll see. Like it's
2 hours on one.
no, yeah.
Low key.
Do you know the format yet? Like how it's gonna be, how many questions, long answer, short answer?
I think 4 questions. Maybe Fateme Swati, do you want to say something about that?
So it's not finalized yet, but we have multi problems, like sub-problems of short answers and long answers, and then we have some that we should solve, and that takes more time. But there are no derivations, but yeah, no derivations.
But we haven't finalized it yet, so yeah. Thanks. Okay, let's try to finish a bit here. I know I haven't given you a break, but I think it's okay. Yeah, we don't need a break. Okay, because we still.
Okay. I want to get this.
Is it clear?
Yes.
Yeah. Yes. Okay. So let's see what we got. This whole thing cancels out. It's just 1. So when we multiply something by 1, we just remove it. Yeah.
It's sums to 1 because it's the probability that for any of these other variables that are going to be in any of the other clusters, so that is a total of 1.
Yes, because we sum over all the values of k for each of these. We sum over.
And you
Yes.
have to end up in one of them, so that adds up to 1.
Yes,
for all
yes,
of them.
yes, 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 yes.
'Cause 100% of the data points are in some cluster.
Yeah. Yeah. Okay. So let's see. Okay, let's try to move on a bit. I know, or not? Is it not clear?
Yeah, I mean, I have only one question. If inside sum is 1, then ultimately it reduces to I is equals to 1 to n log of rest.
This is like this. Is that clear?
Also becomes 1.
No, just these terms, just this. Because we sum over all of these, and all of these cancel. All of these become 1.
Yes. So ultimately it will be I is equals to 1 to n, then log of the rest of the term.
Say that again.
What is the term here then in terms of log? What is the summation
So
left?
that last sum, it gets some of these.
What is this summation for?
No. After we equate these to 1, what term after that? The log the next equation.
Oh yeah. Well, I was gonna write it now. I need to erase something. I guess.
Are the whiteboards not, are the blackboards not movable?
Oh, are they not?
They
Oh.
look like they should be.
Yeah, usually they
Oh,
are.
nice. Whoa.
They're not recently greased.
Oh wow. Okay. So what are we left with? Oh, another question.
So the sum of over k of I of z of I, is that term also 1 that we factored out? It's not?
No, because we have these other functions. Because this is yes.
I see, but by itself it would.
By itself, it would have been. It would have been exactly. But it's because we have these other terms. They screw us up here. Okay, so what are we left with? What is our omega so far? So we're just left with the top. This top row. That's it. That's what we're left with. Yeah. So much simpler, right? Sum over all the data points. Sum over the clusters for data point I. We sum over all the possible clusters that data point can have over that. Not too difficult. What do we do now? So we want we have omega. Well, it was here. And we're trying to find the maximum over that, or over mu of omega. Right? So remember we're trying to mu or t plus 1 is equal to argmax over mu of omega, right? Of this whole thing, which is so how do we so let's say this is a function of mu, right? This omega. So how do we optimize a function when we try to find the maximum value? Take the derivative and set it to 0. Yes. So this is what we're going to do. So we do d over d mu of omega of mu equals 0. These are, we apply the first order conditions. So these are the first order conditions. Okay, so what do we get? What if we, so let's do that. So d over d mu, and we'll do, so we'll do for a particular cluster k, just to simplify it. So we won't do for all the mu's, we'll do for a single. Remember, mu is a vector of multiple clusters. So we do for one single cluster, mu k. Yeah. So d over d mu of sum over our data points times the sum over all the values, sum over all zi, but let's put it over k, which is our our particular all the clusters K that this can have. No, I'll do a different one. I'll do K prime because we have K already here. So P of Zi equals K prime times Xi mu sigma pi log P of whatever we had, Zi given Xi mu sigma pi. Sorry?
Mu k, xi mu k, mu sub k? And because we're doing it for specific.
Sorry, yeah. No, yeah, that was a mistake. So it was like this, no? Yeah, P of Xi given. So I can write it even more precisely. So even Zi equals K prime because it's the same. So it's the same given pi. P of Xi given Zi equals K prime mu sigma pi. So I just rewrote this term here, and now the only thing we have extra is this derivative with respect to mu, the mean. Yeah, question.
That became to 1, right? Why you are writing it again?
We're not writing it again. I just wrote the top part, this top row, not the bottom. The bottom one becomes 1. Just this bottom row. The top one does not become 1.
Substituting the top one with the bottom one.
No, we're not. No, I just took omega is just the top one now. Omega is just the top row because the bottom one cancelled out. So we just had the d over d mu of omega. So what do we do to this construction? We say it's equal to 0. Well, yes, all of this is equal to 0. All of this. But what do we do next? So, what's the next step? Any ideas?
Project rule?
What?
Project rule. Get rid of the project rule.
Product rule.
Product rule.
Yes.
What is that? Or maybe kind of, first even the sum rule, maybe not even the product, no? Or because we have sums. Yeah, well, one of, I don't even know which, exactly which ones. But the derivative of a sum of products, or the derivative of a sum, the derivative of a sum is a sum of derivatives, right?
Mm-hmm.
Yeah.
So we just push this operator inside the sums. So derivative of sums is, we can write it as sum I equals 1 to n, sum over k prime of the derivative. We can put the derivative here now. So we just pushed it inside the sums of the rest. Yeah? And we, for some of you, I explained this a bit in the office hour. So a couple of you would know. So the derivative, so here, from going from here to here, why I applied this f prime, is f plus g prime is f prime plus g prime. This is what I applied, that rule. And now, what about this term? Can we push it even inside here, this term? Can we push it even to go up to here, this derivative operator? Yes or no? Yes or no? So let's do a few things. Like, is this mu k related to this one, bound to this mu here?
Oh, well, it's one of them, right? Because that mu is a vector, right?
Yeah, one of them. But remember something. This was from the iteration t minus 1, all of them. So actually, these are fixed. they're not bound.
It's independent.
Yeah, it's independent. So it's only this one that. So this mu k here would only be bound to one of these mu's here inside this vector of mu's.
Okay.
So this is a constant with respect to, you know, as far as the mu k is concerned. So we can even push it further inside. So I'm even cutting it off from here, and I put it here instead. This so we write p of zi equals k given xi mu sigma pi. So I wrote this, and now I put a derivative all the way here. d mu k of log p of zi equals k prime given pi, p of xi given zi equals k mu sigma pi.
Is that Z1 equal K?
The I,
Oh,
I for iteration I. Zi equals k xi. There's no more ones or there's no z1. It's just zi.
Okay.
We're just working with zi's and xi's now.
It does mixed up with the lowercase I with a 1.
Is the outer, the probability on the right, is that zi equals k or k prime?
K prime, yeah. Yes, because this index is different from this one. Yes. Question, yeah?
Just to be sure. So every time we see a parameter outside the log part, it's the previous iteration.
Yeah, in this case, because these are all coming from that. They're coming from the previous iteration, from the expectation. That's why, and they're outside the log. Outside the log, yeah. But everything inside would have been. Okay. Yeah.
Can you repeat the reason how the derivative went past the
So from here to here, I applied this rule, the sum rule, and also the constant rule. Like so the if you have a constant that you multiply with a function and you take the derivative, it's c times the f prime. So c, the derivative of c times f is c times the derivative of f. Can you see here? So I applied the first rule to push it all the way to here, the sum rule, and then I apply the constant rule to push all the way here because it's a constant. This is the c. Yeah? Okay. How are we doing with time? I'm trying to be 6 minutes.
10 seconds left.
10 seconds?
No, 6 minutes.
6 minutes? What time is it?
19.
Ah, okay. Wow. So there's several things we can do here because we have 5 minutes left. And of course, we'll in the next hour, of course, I'll go through exercises, more like something for a midterm. But I thought this was important to kind of go through because it touches a lot of concepts and it helps with the assignment, which is due in 2 or 3 days.
Do you get an extension on that?
Yes, we need extension.
Push it back 1 or 2 days?
I'm happy to give you extension. I'm happy to, but you have to prepare for the midterm as well. So if I know, so it's if you want, I'll be happy to give you extension on this. Yeah.
Yeah, do it like 1 or 2 days, like
Okay.
the weekend.
Yeah. Send me a few emails just to get an idea of how many of you need it, and like I'll judge on that.
Sorry,
Send.
let's do a mass email.
Okay. What do we do now? Okay, so we just here's before, just to clarify some key concepts. Why are we doing this? Why are we kind of pushing this inside? What's the whole rationale?
Less calculations to do.
Yeah, but a bit more like we're trying to get close to the bound parameter here. Get this operator, which is so far away now. We're trying to get it closer and closer to this this mu here, which is actually where it binds to. And if you take that derivative, if you get there, and if you take d over d mu k of mu k, that will be 1. That just turns to 1. So then like everything else, that's why we're doing all of this. We're trying to push it as close as possible to this bound parameter. So now we got much closer.
Now we can break the log.
Yeah. So now
And then we can do the
yeah,
again.
yeah. So log of a times b is log a plus log b. So we can do the push it even further again. Exactly. So this would be d of log this plus d of log that.
And then, but the first term is just going to be
A constant. 0, exactly. So that one, exactly. So that one cancels out. Yes. So we have only this one. And there's something, so there's another key step you have to do here. which is, so the question is, will this delta mu k affect the terms for which are not equal? Like, you know, if delta mu, remember we have many mu's, right? So will this affect the other ones? For example, the mu1, mu2, which are different from k, like, you know. Well, it would give 0, right? Because when we take the derivative of that, this will be. So remember, we sum over all these k primes here. So actually, let's rewrite this to understand. So what does this mean? This is p of xi. So we rewrite it as. So now we actually rewrite this term by actually instantiating with the model. So p of xi given this is n of xi given mu what? What's the likelihood in terms of the Gaussian distribution? Mu what? Mu k prime, exactly. Mu k prime, sigma k prime. Because this is zi equals k prime. This is the cluster where we sample from. So notice now how, so okay, so
the p of xi given zi mu sigma and pi.
So like you take the big N out. Okay, now
yeah.
This is a little bit.
Yeah. So you'll notice that when k prime is different from k, these terms will be 0, because they won't even mu k won't appear in the other ones for a different k. If it makes sense. So what this means is that, well, I don't know if I have space to write it here, but it's, I'll write it here again. So you have the sum again from I equals 1 to n. And now instead of summing over all clusters k prime, we simply use cluster, because that's the only term that we use cluster k. That's the only term that will still be remained in the derivation. So when k prime is actually equal to k, that's the only term that will be there. So we'll just do p of zi equals, oh, this was k prime initially. So now this becomes k given xi mu sigma pi times d over d over d mu k times log n of xi given mu k sigma k. So the key thing is now this sum disappeared over k prime. That sum disappeared because all those terms will become 0 because of this derivative operator. All the terms for which k prime was different from k disappeared. and you still have to do it. So this is not finished, because we have to now write out the formula of the Gaussian distribution, expand that, push the derivative operator inside. But I'll leave that as an exercise for the rest, for your homework. And you have to do the same for pi as well.
But it's going to essentially be all the same steps.
It's the same steps. And then you have to do the same thing for pi, remember. So the same thing, but it's exactly the same steps, just for pi instead of the proportion, or theta. In the slides it was called theta, but it was the same parameter, this theta. It's the same steps. Any questions?
To me, it makes sense, more better sense than the first thing.
Yeah. Okay, so in that case, I'll see you on Thursday, and we'll go through some exercises for the midterm.
Was there a A4 sheet on the exam?
Sorry?
Was there an A4 sheet on the exam?
An A4 sheet.
So I got a paper. Can we bring a cheat sheet here? I can check your
Let me. I'll get back on that on Thursday.
Take the linear regression code from last time and then expand on it, or?
No, it's different. It's cluster, right? So you
Yeah.
just cut out all the pseudocode.
Yeah.
Where do you present it? Where do you go when you
I don't understand. I feel like I vaguely understand this equaling 1. So it's just we're adding across every single cluster. So I guess what confused me just a little.
I can explain a bit more on this. Go ahead.
So in this part, we're going the summation of the probability of Z1 given these, and then Z2 given all those.
No. So it's a product. P of Z1, P of Z2, P of Zn, apart from the Zi.
And so you product all these together, and then when you iterate with this sum, how does that?
So here's something you can put it back together. For example, if you want to conceptualize it easier, this is P of Z1 because comma Z2 comma Zn because of the joint, and then you sum over all those, and that becomes 1. That's one way to see it. How does this become 1? So imagine if you had only one term here, not. It's clear how it becomes sum over Z1, sum over that. It doesn't matter if it's a conditional. It's still a distribution, so it will sum to 1 regardless. If you have 2, what happens is we do exactly this. Exactly like, if you can come.
Yeah.
So now we have 2, sum over Z1 and Z2 is this. Becomes all these 1, 1, 1, 2, 2, 1, 2, 2. And you can rewrite it as this. You can push one of the summations for Z2 inside.
Yeah.
And now this becomes 1. No, look at this. Now
the probability of Z2 is any of
you can put a square bracket. This is exactly what this means. So you put square bracket inside, so you do this in isolation. And this is 1 because you sum over Z2. Sum over Z2 of P of Z2 given next to this 1. It's a distribution.
So then, just looking at this one, this is like Z1. I was just looking at the inner part of this summation. It's just so we pick out one of them, Z1, and they're saying all of these are going to add up to 1, and then we're going to multiply. Oh, I think I see it. Back. I think I see it.
It's as if
this is one value for Z1 through Zn minus I. Here's one value and the probabilities for all of them, and then move on to the next value for all of them. And if you sum all of them, and because these are all multiplied,
multiplied. Yes,
it'll
yes.
be whatever it is. But then you add it all up, and it adds up to 1 for all of them.
Yeah.
I see. So we're okay. I think I get it.
Another way to see it, you can. What if I move the Zn, the summation of just Zn inside here at the end? So I can do that. Like, it's the same thing. I was doing that. So now